This lesson is on differentiation of inverse trigonometric functions. So, inverse trig functions or arc trig functions, finding the derivative of those and applying those situations. The first thing we're going to do is we're going to review our inverse trig functions or our arc trig functions. You don't spend a ton of time in your pre-calculus coursework working with these. So a brief review of what they are, what they mean, their notation, and then we'll go through the calculus of deriving these types of functions. So remember, you have all 6 regular trig functions have an inverse function. Y equals arc sine of x, arc cosine of x, arc tan of x, cosec, sec, and cotan. All have arc functions or inverse functions. Same exact thing, just different notations. Sine to the negative 1 of x are called inverse trig functions or arc trig functions. This isn't 1 over sine of x. This is the arc sine of x. So this notation over here with the negative 1 exponent is sometimes a little confusing. So realize when it's a trig function, you have that negative 1 up there. That means it's an arc trig function or an inverse trig function. Inverse trig or arc trig wants to know what's the angle. That's the question an arc trig or inverse trig function is asking you. What's the angle? So if it says y equals arc sine of x, it wants to know what's the angle that has a sine of x. So in this case, when it's inverse trig function, the y value is actually the angle. What's the angle? Now, because trig functions are periodic, the wave function's up and down, or the tan function repeats itself, their inverses aren't functions on their own. All right? They fail the horizontal line test, so the inverse will not be a function. So if you remember back from your pre-calculus work, the inverse trig functions are only defined on a certain domain and range, on certain pieces. They take certain pieces of the regular trig function, and that's how they define the inverse trig function. So if you look up here, here's a review. Here's your arc sine of x, your inverse sine graph, and its domain is negative 1 to 1, because that's the x values. The sine can only go from negative 1 to 1 on the y, so the arc sine can only go from negative 1 to 1 on the x. So you're going from negative 1 to 1. And its range, they took the piece of the sine function from negative pi over 2 to positive pi over 2. One complete cycle from top to bottom, so it hits every value in between. So the range, since they took that on the x value on the sine function, that'd be the y value of the inverse sine function. So the range of the inverse sine is negative pi over 2 to positive pi over 2. And they did a similar thing for all the other 5 inverse trig functions. Domain for arc cosine is negative 1 to 1 also. Range, in this case, they took from 0 to pi for the arc cosine. Domain of inverse tan, if you think about a regular tan, starts down here, curves, goes all the way up. So that goes from negative infinity to infinity on the y, so the domain of the arc tan, or the inverse tan, is negative infinity to infinity. The range from negative pi over 2 to positive pi over 2, that's the chunk that they took and defined as the inverse tan, or defined to use the inverse tan. Now for secant, arc secant and arc cosecant, since the sine and cosine can only be between negative 1 and 1, well, 1 over those has to be outside of those ranges. So the domain of the arc secant and arc cosecant is x has to be either greater than positive 1 or less than negative 1. It has to be outside of 1 and negative 1. So domain of, this one's arc secant here, domain of that is x is less than or equal to negative 1, or x is greater than or equal to 1. The range is y is between 0 and pi, but it's undefined at pi over 2. And you have these other 2 here you can look at. This is a refresher. You know, this isn't vital for the calculus portion of this, but this is a refresher of where this stuff comes up, and especially when we define the derivatives of arc sec and arc cosec, this is important for that proof. Okay, again, inverse trig wants to know what's the angle. So sine -1 of -1/2 or arc sine of -1/2 wants to know what's the angle with a sine that's -1/2. What's the angle that has a sine of -1/2? What's the angle that has a sine of -1/2? Remember, the range of arc sine is from -π/2 to +π/2. So we have to pick a value in between -π/2 and +π/2. And that happens at -π/6. More than likely, when you think of arc sine of -1/2, you think of 11π/6 is the first one that comes to mind. But that's not on this range. So you have to figure how's that written as a negative angle, and that's -π/6 down. Okay, that was a review of your arc trig, your inverse trig. Now we're going to use that review to define a couple of derivatives of these functions, and then I'll give you the rest, which can also be proven in this method. So if y equals arc sine of x, that means sine of y equals x. If y equals the arc sine of x, what's the angle that has a sine of x? That means y is the angle, so the sine of y equals x. Rewriting it like this allows us to derive it a little easier. We're going to derive this with respect to x. We're going to find y prime or dy dx, so we're going to derive both sides with respect to x. The derivative of sine of y is cosine of y, but because we're deriving a y term, we have to use implicit differentiation and multiply by dy dx at the end. Derivative of x is just 1. So cosine of y dy dx equals 1. Divide both sides by cosine of y. You get dy dx equals 1 over cosine of y. That can be written as secant of y, but as you'll see when we get to the simplified derivative, leaving it like 1 over cosine in this form is going to be a little bit easier for us. Now, in order to find the cosine of y, we need to make a right triangle that fits this description. So that the ratio, the sine of y, is equal to x. Remember your trig functions, sine of an angle, if you're talking about right triangle trig, is written as the opposite side, the length of the opposite side, divided by the length of the hypotenuse. So that ratio, if y is your angle, this angle in here is y. The length of the opposite side, divided by the length of the hypotenuse, is going to be x. So the opposite side over here, hypotenuse here, so it's going to be x over 1. Remember, all we're worried about is the ratio here, the ratio of this side to this side. Because we want to find the cosine, we just need the ratio. We don't need specific values. So this ratio is x over 1. Using Pythagorean theorem, you can find this bottom side, this missing side. That side's going to be square root of 1 minus x squared. This squared plus this squared equals this squared. Go through Pythagorean theorem, you should be good with that. So, the cosine of an angle is the ratio of its adjacent side to its hypotenuse. The adjacent side to y is square root of 1 minus x squared. The hypotenuse is still 1, so the ratio is going to be this side over this side. So, the cosine of y is going to be square root of 1 minus x squared over 1, which is just square root of 1 minus x squared. So the derivative of y equals arc sine of x is going to be 1 over the cosine of y, which is 1 over square root of 1 minus x squared. So we rewrite this in normal trigonometric terms, derive with respect to x using implicit differentiation, simplify, use a right triangle to figure out the ratios, and get our derivative in terms of x. We're going to do a similar method to find the derivative of y equals arc tan of x, the inverse tan of x. Again, we'll rewrite it. Tan of y equals x. Derive both sides with respect to x. Derivative of tangent is secant squared of y times dy dx, because we had a y term we were deriving. Derivative of x is still 1, so I get dy dx equals 1 over secant squared, which is the same as cosine squared of y. So we're again going to use a right triangle ratio is opposite side divided by the adjacent side. So x is going to be the opposite side. The adjacent side will be 1. So that ratio is x over 1. Remember, all we're worried about is the ratio. In order to find the hypotenuse, again use the Pythagorean theorem. A squared plus b squared. Take the square root of that. So your hypotenuse here is square root of 1 plus x squared. I need the cosine of y. Cosine is adjacent over hypotenuse. So the cosine of y is 1 over square root of 1 plus x squared. But the derivative with respect to x of arctan of x is a cosine squared. So we're going to square that ratio. So dy dx is 1 over square root of 1 plus x squared, quantity squared. Square a fraction, square the top, square the bottom. 1 squared is 1. Squaring a square root cancels out. So the derivative with respect to x of y equals arctan of x is 1 over 1 plus x squared. You could go through the other 4 trig functions and find their derivatives exactly the same way. Rewrite, derive with respect to x, simplify, solve for dy dx, make a right triangle and go through and find that derivative in terms of x. Remember, on our derivative in terms of x. I'm not going to go through every one of those. We're going to, again, use the chain rule with our derivatives here. So the derivative of arcsine of u is going to be u prime over square root of 1 minus u squared. So it's the same as with the x, except on the top you're dividing or multiplying by that u prime. You're multiplying in the end by the derivative of that angle. If it's not the angle, of that value. If it's arcsine of something other than just an x, you have to use the chain rule. So you multiply by the derivative on top. It's still the same exact thing. Down here will be squared. Arctan, same way. U prime over 1 plus u squared. Arcsec's a little bit different. Derivative with respect to x of arcsecant of u is going to still be u prime over. You still have a square root of u squared minus 1, but you also have an absolute value of u on the outside. We could go through and prove this. I'm not going to here. You may see it in class. The absolute value sign, it just shows up out of nowhere there. It has to do with simplifying this based on the domain and range of the arcsecant function. It turns out that if you went through this, the value would always have to be positive. So instead of writing 2 different answers, they just wrote an absolute value sign there to accommodate for that. Nonetheless, there's the derivative of arcsecant of u. Now I only gave you 3 here. Arcsine, arctan, arcsec. Because the derivatives of arccosine, arccotan, and arccosec are all the exact same as these, except with a negative value. When you derive arccosine, arccotan, arccosec, any of the cos, the derivatives are going to be the exact opposite of these. Meaning they'll be the same thing except negative. Have that list there. So you do have to memorize all 6 of these, but 3 of them are just the opposites of the originals. Do a couple problems here, deriving arc-trig functions, and that'll be it. So y equals arcsine of 8x. Derivative of arcsine of u is u prime over square root of 1 minus u squared. So the derivative of this over 1 minus this squared. Derivative of 8x is 8. Over the square root of 1 minus that, 8x squared. 8x quantity squared is 64x squared. So you get 8 over square root of 1 minus 64x squared. Derivative of arctan of x. Derivative of arctan of square root of x. Derivative of arctan of u prime over 1 plus u squared. So the derivative of this over 1 plus this squared. Derivative of x to the 1/2 or square root of x is 1/2 x to the negative 1/2. 1/2 x to the negative 1/2 is your numerator. Denominator is 1 plus square root of x squared. So 1 plus x. You simplify this. 1/2, the 2 goes in the bottom. Square root of x goes in the bottom. And that whole thing multiplied by 1 plus x. You may see some books distribute this through, or some multiple choice tests, making this 1 over 2 square roots of x plus 2x to the 3/2. They distribute that through the parentheses. Either way, it's still an equivalent form. And last one here, derivative y equals arcsec of e to the 9x. Remember, arcsine, arctan, and arcsec are the 3 positive inverse trig functions, or 3 inverse trig functions where the derivative is positive, and then the other 3 are the same thing, except they have a negative derivative. So that's why I went through just an arcsine, an arctan, and an arcsec. So, derivative of arcsec is u prime over absolute value of u times the square root of u squared minus 1. So, derivative of e to the 9x is e to the 9x times the exponent, so 9 e to the 9x over absolute value of e to the 9x times the square root of e to the 9x quantity squared minus 1. 9 e to the 9x stays. Absolute value of e to the 9x, well, we don't need the absolute value because e to any power is going to stay positive, so I leave that as e to the 9x. Square root of e to the 9x quantity squared, power go power, you multiply the exponents, e to the 18x minus 1. And now here you see you can simplify this e to the 9x, this e to the 9x will cancel, and you're left with 9 over the radical. So, these type of functions don't show up a ton, but this is another type of function that does show up from time to time, and you do need to have committed to memory these derivatives, and again, it's just opened up another set of functions that we can find the derivative of. We can find the rate of change of. We can, apply all those old rules, relative extrema, optimization problems, whatever. Anything we've done in the past with differentiation, we can now do the same thing with inverse trig functions.